So Ramesh, we've seen the fundamentals of interrupts, but can you show me a real example of an interrupt?
Yes, let's take a look at SysTick because SysTick is a fundamental device on all ARM processors and it supports interrupts.
It does.
So you recall we use SysTick for a delay. Now we're going to use it for doing interrupts. Just to recap, we saw what our devices registers were. These are our memory mapped registers. The three registers of interest to us when we were doing just the delay, we only focused on these. Now we're gonna introduce some more things, and more importantly, when we were working on delay, we said we will enable the interrupt, we will choose the proper clock, we'll enable the device, that is, this is my start stop, this is my source, which can be an external or internal, and that's the count. And this was the key. This was a flag that we repeatedly polled. We were using polling. That is, we were checking to see if this flag was set or not.
So who sets that flag, hardware or software?
So the hardware sets the flag. And we know how that flag is set because that's where these two other registers come in. So we said that there's a load register, and the load register has a 24-bit value in it. Bit 23 to 20, it has a load value, and this is whatever our repeat value or reload value or initial value or whatever we want to call that. That's what our time tick start point is.
Okay.
And then we had this register called the val register, and the val register is the one that is showing your current value that the counter has. It's also a 24-bit, right?
Okay.
So the way it was working is we would take what is in the init, and that becomes a start point, and this guy counts down. Let's say this was, for example, we started with a value of 500, we go 500, we go 499, and we keep counting down all the way from 1 to 0, right? And this act of going from 1 to 0, that is the point where we know that our counter has hit 0, so we'll make this count be equal to 1 at that point.
And then what happens after 0, Ramesh?
So after the 0, then immediately after the 0, this guy needs to get back a new value. But where does he get its value? He reads it from there and gets it back.
Now, does the software make that happen, or is that a hardware thing?
That is still a hardware thing.
Nice.
This is automatically
So
done.
it just goes over and over and over.
Yes.
All right.
And when we were doing delay, a subtle point that we noted is that that this flag, once it's set, the only way it'll become 0 again is if you read this register. The act of reading this register will automatically set that back to a 0.
Ah, sweet.
Right. So you when you check it and say what is it, and you see it that it's no longer it is a 1, the act of reading it will set it. Right. That's how we know.
Yeah, but what about interrupts, Ramesh?
So what about interrupts? So how does interrupt work in this whole thing? So let's look at the fact that we still want to initialize this, but now we're going to initialize it slightly differently. So this is our key flag here. This flag used to be a 0 because we didn't enable interrupts, but now we're going to enable interrupts. To enable, we'll write a 1 to it. And so in our initialization, in some sense, our control register in initialization is now going to be a 7 rather than a 0, because we'll make these 1, 1, and 1. Yep. So we'll put a 7 there. So that's what it'll be. That's the fundamental one simple change. Now we also have to decide what should be our initial value, and we know how this decrement happens, and we kind of already saw this. But when we actually decrement, this decrement of -1 is done every delta t, and then it goes back. So this delta t for us is 12.5 nanoseconds if we are operating at 80 megahertz.
I see.
Let's say our initial value is an n.
Got it.
So now it means that this, once I set the value of n, it's going to count n minus all the way from n to n minus 1 all the way down to 0, which means it's actually going to count n plus 1 times.
And then after 0, It starts back over
starts
to N.
back over at n. So
Okay.
the total number of ticks is actually that. So that times 12.5 nanoseconds is how long it's going to take between interrupts. This is the time between
So what caused the interrupt again?
interrupts. Okay, let's take a look at what caused the interrupt then. So the interrupt itself, now this flag that we were setting, this flag previously when we didn't have this bit on, this flag was just being set. But now it's doing two things. It's going to set this flag like before, but in addition, it also causes an interrupt. This transition now causes an interrupt. And what specific interrupt does it cause? Causes a SysTick interrupt. And there are many interrupts in our system like we saw, but this is SysTick interrupt. And that specific interrupt, we want to handle that. And so we'll see how we handle that. But one other thing we do as far as interrupts is concerned is we also set the priority. So this is the second thing that we do, which is the priority. And the priority on our MSPM0 processor is a 2-bit number, so it can take values from 0, 1, 2, or 3.
All right. What do the numbers mean?
And on most systems, always, this is always the highest priority, and this is the lowest priority. So we have to choose a priority for our SysTick, and we can choose any of these, and we're going to choose a priority of 2, let's say.
Okay.
And that will be the SysTick priority that we choose.
So that means a priority 0 or 1 interrupt could actually interrupt a SysTick.
SysTick.
But
Yes.
priority 2 and 3 would then be postponed.
Postpone, and they're put on hold, but they're not lost.
Got it.